What's up, folks? This is Ref Bari, Brown University physics grad student. Welcome to the next episode of Quantum Field Theory. Today we're discussing the Feynman Propagator, one of the most famous building blocks of QFT. In fact, it's so famous that I've got it laser cut right here on this wooden board. So by the end of this video, you'll have some basic intuitive understanding of this equation. I'm not going to go through the full derivation in this video just yet. In this video, my goal is to give you a kind of intuitive understanding of what exactly this equation, this Feynman propagator here, is describing. So, without further ado, let's get started. The Feynman propagator, there are many different ways to motivate this fundamental building block of QFT, but maybe one first way to motivate it is by considering an interacting system. Here's what I mean. Let's say that we have a box. This box has some atoms inside of it, some atoms that are interacting with each other. So this could be a box of, for example, n electrons, okay? So you could have n interacting fermions, for example, electrons or bosons, and interacting fermions or bosons / bosons. So the point is you've got a box of particles, and this box is in its ground state. Let's say, just for the moment, that is it's in its ground state, ket sigma. So now let me ask you a question. Is there a way we can probe the dynamics of the ground state of this system? Well, indeed there is. Well, we can shoot a particle at this system and see how that particle interacts with the ground state of this system and see whether that system is still in the ground state after that particle leaves the system. Here's what I mean. So we can shoot a particle at our system, and then after the particle leaves, we can examine if our system is still in this ground state ket sigma. So the way we do that is, the way we quantify all of this is as follows. Let's say that at some space-time point y, mu, which corresponds to a time y0 and a space-time position with a vector y, let's say we create a particle at this space-time coordinate y mu, okay? And then this particle interacts with our system of n fermions or bosons, and then the particle comes out the other side, and we're going to annihilate this particle, okay? It's going to get shot out the back, and it's going to get annihilated at some space-time coordinate x mu, which has a temporal coordinate of x to the 0 and a position coordinate of x. So the question is, what is the probability that our system is in the ground state even after our particle has interacted with it? Okay, so let me write that question down. Question: what is the probability? So it turns out the answer to this question right here, what's the probability that our system stays in the ground state, is answered by the Green's function. By the Green's function. You don't have to know what a Green's function is, okay? I'm just going to say that this question, the answer to this question, turns out to be, okay, your initial state, which is the ground state of your system, okay? And we're going to find the overlap integral, okay? You should know these words, the definitions of these words if you've taken quantum mechanics before, but essentially what we're trying to find is the probability that our system stays in the ground state even after the interaction. So we take our initial state and we take the inner product of that with our final state, which is still in the ground state, okay? That's the question we're asking, that the initial and final states are both the ground state, even after we have created a particle at some space-time coordinate y mu and annihilated that particle at some space-time coordinate x mu. So this is the answer to our question. And in fact, this little computation is so famous, we call it the Green's function, okay, of x mu comma y mu. Okay, so now we have to start making this answer right here. This is just a pictorial kind of qualitative answer to our question. Now we have to start making this a physical quantity. We have to start applying some quantitative physics to this. Okay, so how do we break this down? Well, first of all, I can express the creation of a particle using the creation operator, and the annihilation of a particle using the annihilation operator. Okay, so in other words, instead of this happy face, I can write phi plus, okay, phi plus, meaning that a particle was created at y mu. Okay, and likewise, I can annihilate a particle using the annihilation operator phi x mu. Okay, and then I've once again got my initial and final states, and this is equal to the Green's function. This is called the two-point Green's functions because there are two scalar fields that are creating and annihilating our particle here. Okay, so now let me ensure that this is okay. So now the next thing we're going to do is enforce causality. Now this is something that you don't often have to think about when you're in undergrad physics, but in this case we do have to consider it because we're in relativistic quantum mechanics, and in relativity causality is all important. So in this case we'd like this event, the creation of the particle, to be before the annihilation of the particle, right? I mean, you might think that's obvious, but we've got to enforce it somehow, right? So in other words, we'd like y0, the temporal coordinate of this space-time point, to be less than x0, the temporal coordinate of that space-time point. So we'd like to enforce the fact that y0 is less than x0. And how do we enforce that? By multiplying this Green's function by a Heaviside function, y0 minus x0. Now, it could be that this is actually x0 minus y0. Maybe that's the thing that enforces this condition. The point is there's a Heaviside function that enforces causality. Don't hold me at gunpoint as to what the sign of this Heaviside function is. That doesn't matter. So now the next thing we're going to do is we've got this Green's function so far. We've enforced causality. And the next step is to expand this thing by considering antiparticles. Okay, so what do I mean? Well, Richard Feynman looked at this Green's function and he thought for a long time about how to incorporate antiparticles into the picture. Okay, so here we're creating a particle here and annihilating a particle there. Is there a way we can introduce antiparticles into the picture? Because we really do need antiparticles to enforce causality in its full scope. Okay, there's a long proof that goes with that. We'll explore that in future videos, but that's the main idea. Somehow we need to introduce antiparticles into the picture to enforce causality in its full scope. So the way we can do that, Richard Feynman figured out after many computations, is that we can consider the opposite case. What if we have the creation operator here and the annihilation operator here? In other words, what if we have plus, okay, our final state and initial states are again the same, they're still sigma, the ground state of our interacting system. But now we're going to place the creation scalar field operator here. These are all field operators, and okay, so this is y mu, and our annihilation operator over here. Okay, and we're going to enforce now that x0, we're now enforcing the opposite case, which is when x0 is less than y0. So this case held when y0 was less than x0. Okay, this was the case when the temporal coordinate for the space-time point y was less than that of x, and this is the opposite case for the antiparticle picture. Okay, we will draw diagrams I will draw diagrams explaining how this explains antiparticles, but you'll just have to be patient for a little bit. I know it can be frustrating when you see an equation and it looks strange at first, but don't worry, we'll look at many different interpretations, different derivations for the Feynman propagator. It will all make sense, so I'm just asking you to be patient with me, bear with me, but this is what we have so far. This is what we have. We have the particle component of the Green's function, and we have the antiparticle component of the Green's function. Okay, and we have these Heaviside functions enforcing causality in either direction. And so now my next step is going to be to use the mode expansion of the fields operators to really kick this thing into high gear. Okay, so let's do that. And actually, before I do that, I'd like to do something else as well. Okay, I'd like to show you what this is really doing. Let me focus on this first term in the Green's function. Let's focus on this first term, causality and all. Let's focus on this over here. And let me write this exact same line over here. So I've got my interacting system ground state, okay, and we've got our scalar fields operator, which is annihilating the particle at x mu and creating it at y mu. And we've got our initial state, which is also the ground state of our interacting system. Okay, I'm just going to ignore this causality for now because this is just added to this. Okay, so now look at this for a second. First, let's consider the case where we have a non-interacting system, where all the particles just pass through each other. In that case, this ground state will actually be the vacuum. Okay, it will just be the vacuum state, ket 0. Okay, let me now put these things back. And phi dagger y mu. Now let's try to understand how this is actually creating or annihilating a particle. Okay, so if I look at this for a second, then perhaps we can focus on this component, phi plus y mu acting on 0. Now what is the modal expansion of phi dagger y mu? Let's write the modal expansion down. So there's no need to memorize any of this. This is all intuitive. So we've got the integral. Okay, the modal expansion is in essence a Fourier transform. Okay, we've got the integral over momenta. Okay, now because it's a Fourier transform, it's occurring in 3 dimensions, maybe 4. Who knows? Don't shoot me in the face. But we've got 3 factors of 2 pi here by virtue of the Fourier transform, and then we've got a square root, oh, by the way, this should be 3 halves. We've got a square root of 2 EP. Where does this come from? This is exactly analogous to the position operator for a simple harmonic oscillator. This is exactly where that comes from. Another way you can motivate this factor of 1 over 2 square root of 2 EP is by using the mass shell of a relativistic particle. Anyway, to keep on going, so what you have over here, all of this, is essentially the integral measure, the Lorentz invariant integral measure that makes this fields operator Lorentz invariant. Okay, it doesn't change as when you change reference frames. So we've got that, and then this is a creation field operator. So it's going to create, so let's see. It's going to create an outgoing particle. So it's going to create an outgoing particle. So that's e to the IPX. Okay. Oh, this is at y. So I should put y instead, not x. And it's going to annihilate an incoming particle. So now think, if this is a complex scalar field, then I'm going to annihilate an antiparticle that's incoming. So it's going to be e to the minus IPY, where B represents the antiparticle that's being annihilated. But on the other hand, if I have a real scalar field, then this will simply be, let me use my other hand, this will simply be, once again, A sub P. So depending on whether or not you have a complex scalar field or not, you're going to either annihilate a particle that's incoming or an antiparticle that's incoming. So let's say I have a complex scalar field. So we're going to annihilate an incoming particle. Okay, so now let's go ahead and act this on the vacuum, ket 0, right? So what's going to happen? Well, let's take a look at what AP dagger, okay, acting on the vacuum does. And we've got e to the I p dot y plus b, oh, wrong color coding, b p, and these are all vectors. I should mention these are all vector quantities. bp acting on 0 and e to the minus I p dot y. Now this is of course a creation operator. It's going to create a particle of a definite momentous state ket p, e I p dot y. But this, on the other hand, is an annihilation operator, and it's going to annihilate this state, giving us 0. And so we're left with a rather simple looking integral here, which is the integral. This is the integral measure, and I've got d cubed p right here. Okay, so very good. So this is what our integral is for phi, our creation scalar field operator acting on ket 0. Now, to figure out the other component of our inner product, which is phi of x mu, the annihilation operator acting backwards on 0, I can just go ahead and take the complex conjugate. Okay, or I can take the dagger of both sides. Okay, or complex conjugate, whatever. I don't know the difference, and I've gotten this far. So if you don't know the difference, that's fine. Well, actually, you should know the difference. I don't. Okay, so now let's take the complex conjugate. What's going to happen? This ket turns into a bra as expected. This phi dagger turns into a phi at y, but I'm going to change all the y's into x's, all the y mu's into x mu's, and all the p's, okay, all the p momentum vectors into q momentum vectors, because p and q are, after all, dummy variables. We're integrating over them. So we've got phi of x. I should write x mu, but at this point it's too late. So this is equal to the integral over the integral measure. I'm not writing this for convenience purposes. And so instead of p, I'm going to have bra q and e to the minus, because remember, I am taking the complex conjugate. I am changing this I to a negative I. I am changing the p to a q, and this is an x. And now I have d cubed q. So now, if I go ahead and sandwich these two things together to create the inner product, so if I'd like to calculate 0, this should be 0 phi x, 0 phi dagger y, then what am I going to get? Hopefully you can see that. Actually, I guess this is not as good as the neon Hagoromo. So this is equal to the integral over d cubed p over 2 pi cubed 1 over 2 ep to the 1/2. And let's go ahead and sandwich these two over here. I have q inner product with p. I've got e to the I p dot y minus q dot x. Okay, and we're integrating over all momenta. So actually this should be d cubed p and d cubed q. And so this is what we have. But now take a look. What is the inner product of two momentum eigenstates? Well, if I'm not wrong, that should be the delta, the Kronecker delta of p minus q. Now, the next question you should ask me is, prove it. Okay, why should I believe you? The way you can prove it is actually rather straightforward. Let's see if there is space. Indeed there is. The way you can prove this is as follows. So I have q and I've got p. Now, I can create a particle of definite momenta q by acting the annihilation operator backwards on the vacuum state, and likewise, but with the creation operator acting forwards on the vacuum state to create a definite state of momenta p. And so now, I remind you of the commutation relation between AQ and AP. Okay, so this should be something like delta 3 Q minus P. Okay, and so now that means you can switch these two at the cost of a delta function. Okay, so let's think about that. Okay, so what have I got here? So if I switch these two, then let's go ahead and write it over here. I'm going to have 0. I'll have AP dagger, AQ, okay, but plus, we're doing this at the cost of adding a delta function. This should be Q minus P, Q minus P. Okay, but now take a look. If this creation acts backwards on the vacuum, that gives us 0. And if AQ acts forwards on the vacuum, that gives us 0. So this inner product right here of AP dagger AQ on the vacuum states, okay, that's going to be 0. And I can just pull out a delta P or Q minus P. I do this every time. Whatever, it doesn't matter. These are just dummy momenta. Q minus P of 0, 0. So this right here is just 0 for the reason we just explained. Creation backwards gives us the vacuum, gives us 0, and annihilation forwards gives us 0. And this is just 1. So we're left with this as desired, QED. So now this delta function is going to enforce P to equal Q. So that means that this Q is now going to become P. Okay? Oh, by the way, there should be one additional factor of 2EQ to the 1/2 here, right? Because we have essentially two integrals with their own independent integral measures. And this delta function is also going to enforce this Q to equal P. And so what integral are we left with? Okay, we're left with the integral of d cubed p. Okay, every q is going to collapse to a p over 2 pi cubed. We're not going to have the 3/2 anymore, just 2 pi cubed times, now we're not going to have d cubed q anymore, over 1, 2 EP. Okay, the halves also go away, right? Because we've got 2EP to the half, 2EQ to the half, but the q's become p's so that they're the same. This delta function enforced all of this q equals p, so it's going to go away after enforcing everything, and we're left with e to the I p. I should write p dot y minus x. Okay, so very good, very good. We've got our first vacuum expectation value. Okay, so this is a VEV, vacuum expectation value. Okay, that's a big deal. These are big steps. So that means that this vacuum expectation value right here, this right here, is equal to this interval over here. Okay, and of course, don't forget, all I have to do now to write out this term is just add on my Heaviside function to enforce causality. Y naught minus x naught. Okay, so that would represent the first term of my Green's function right here. Okay, so I will reserve the second term for the next lecture. If you have any questions or comments or concerns or mistakes or worries, then please comment down below. So thank you for watching. We'll see you in the next one.